Picking up where we left off, now we're going to look at a comparison of standard and off-center rear rims and the effect of spoke tension on lateral stability. Another situation we want to take a look at is a comparison of the Velocity A23 rim, the standard version, with the off-center version. We'll first take a look at the versions of these rims that have a machine braking service, which makes them appropriate for rim brake wheels, and the standard rim on the left can be used either in the front or the rear, and the off-center version on the right can be used in the rear. We want to answer these questions. Is the OC or off-center rim better in a rear wheel than the standard rim? If so, why? And what is the empirical evidence? And specifically answer this question here. When subjected to side loads, does the OC rim reduce the lateral deflection of the rear wheel? Here's the wheel profile seen from behind, the left, the right, the freehub body, and a cassette. Here are the two rim profiles again. There is, of course, a difference in where the holes are located in the two rims. These are in the center, and these are moved to the left. We're going to build up some wheels using this hub, which has an overlock nut width of 130 millimeters. The center of the hub is 65 millimeters from the end. The distance from the center to the right flange is 18.9 millimeters. From the center to the left flange, 34.3 millimeters. And here's a duplicate of that hub. Here we see the geometry of two wheels, obviously not drawn to scale. Put a tire on each one, and the center of the tire is directly over the center of the hub. A spoke length calculating program will give me the exact dimensions shown here. This new dashed line is 3 millimeters to the left of the first one, and it represents where the holes are located in the rim. And that is going to change the length of these numbers down here. To 21.9 millimeters from the new dashed line to the right flange, and 31.3 from the new dashed line to the left flange. Now I can put these lines in here, which gives me 4 right triangles. And from that I can calculate angles on the left. You see those, and on the right, different angles. Now, that vector there on the left diagram on the drive side represents the tension on the drive side spokes, and that is 1,079 newtons for the experimental wheels that I built up. The horizontal component of that is 71 newtons. It will be 71 newtons here also, and that is going to give me a tension on the non-drive side of 597 newtons. Going over to the off-center, once again we have 1,079 newtons, and that gives me a horizontal component of 83 newtons because the angle is wider. 83 newtons over here also, and that calculates out to 761 newtons on the non-drive side spokes. Starting with the wheel on the left, let's look at my vertical components of my tension vectors. That line there is 593 newtons. The longer one on the drive side is 1,077 newtons. On the other wheel, my non-drive side vertical component is 756 newtons, and on my right side it's 1,076 newtons. If I add my vertical components together, on the left I get 1,077 plus 593 is 1,670, and on the right 1,076 plus 756 gives me a total of 1,832 newtons. Now we're going to use these two wheels and my experimental table and do some measurements of side-to-side deflection. Starting with the Velocity A23 standard rim. Here it is all set up for experiments. I've got a very high-end Mitutoyo dial indicator, which has a resolution of millimeters to 3 decimal places. That is in turn bolted to this piece of angled metal, which is clamped securely to a cross beam. And up here I have 2 levels, which I can use to make sure that my dial indicator is perfectly vertically positioned. It was very interesting to note that this dial indicator is so sensitive and so accurate that the act of just putting a notebook, my lab notebook, on the top of the table and then trying to write something into it would change the reading on the dial indicator. With 170 pounds loading the wheel sideways, I have a reading on my dial indicator of minus 0.018 millimeters. When the weight is removed, the hub moves up and I have 2.746 millimeters. So my deflection here is 2.746 millimeters minus a minus 0.018 millimeters gives me 2.764 millimeters. So in summary, with my A23 standard rim with the free hub body pointing down, I get a deflection there of 2.746 millimeters. When I turn it over and run the same tests, I get a deflection of 2.447 millimeters. With a velocity A23 off-center rim with the free hub body down, I get a deflection of 2.623 millimeters. The same rim turned over with the free hub body up and running the same tests, I get a deflection of 2.513 millimeters. Putting it all together with the standard rim, I get these 2 deflections: to the right 2.764 millimeters, to the left 2.447 millimeters. Difference in the extent of deflection of 0.317 millimeters. On the right, putting in the same experimentally determined numbers, I see this, and I have a difference there of only 0.110 millimeters. What this tells us is that for the wheel on the left, the rim deflects a little bit more than 0.3 of a millimeter in one direction than it does in the other direction. Whereas using the OC rim, the difference in the amount of deflection to the left and to the right is reduced significantly, and it's going to be easier to keep that wheel centered in the frame of the bike when subjected to side loads. We've seen how we can beneficially use the off-center rim in the rear wheel of a rim brake bicycle. If I have disc brakes, I can likewise use that same rim in the rear, but I can also turn it around and use it in the front wheel as well. Now, switching gears again, in an earlier chapter I gave you a list of factors that can improve lateral stability: a rim with a smaller ERD, hub with greater flange diameters, a hub with greater center to right and center to left dimensions, and that fewer crossings can give us shorter spokes. And then I added optimal spoke tension, but then I qualified that by saying it would be more accurate to replace optimal spoke tension with adequate spoke tension, as you will see later. Unless the tension is very, very low, adding more tension does not really have the effect on lateral stability that you think it might. An experiment and the data gathered will prove the accuracy of that statement. We return once again to the table. And just to simplify things, let's take out all those numbers and vectors you've been looking at and start with just this picture here of a velocity deep V rim with velocity race hub and Sapim laser spokes. This is going to be my high tension test, and I have a whopping 1,454 newtons on the drive side spokes and an offsetting tension on the non-drive side spokes of 712 newtons. When I apply my 170-pound side load, the tension on my drive side spokes increases from 1415 to 1505 newtons. On the non-drive side, it decreases from 712 newtons to an estimated 200. It's so low it's kind of off the scale of my conversion table. And at the same time, the hub drops 2.9 millimeters. Now we do the same test again, except starting with lower tension of 942 newtons on the drive side and 415 newtons on the non-drive side. When I apply my side load, the drive side tension increases from 942 newtons to 1142, and on the other side it decreases from 415 to an estimated 100 newtons, and the hub drops 2.8 millimeters. Now we turn the wheel over. This will be our high tension test, starting with 1454 newtons on the drive side and 712 on the non-drive side. Applying the 170-pound side load, the tension on my drive side spokes decreases from 1454 to 1114. On the non-drive side, it increases from 712 to 942, and I get a drop of the hub of 2.5 millimeters. At moderate tension, we start with 942 newtons on the drive side spokes and 415 newtons on the non-drive side spokes. Applying my side load, my drive side tension decreases from 942 newtons to about 712, and on the non-drive side, the tension increases from 415 to 736, and we get a drop of 2.6 millimeters. In summary, with my free hub body down and nice high tension on my drive side spokes, I get a drop of 2.9 millimeters. At moderate tension, I get a drop of 2.8 millimeters. With a free hub body up and the same high tension, I get a drop of 2.5 millimeters. And at a more moderate tension on my drive side spokes, I get a drop of 2.6 millimeters. As a summary, we see that the orientation of the free hub body down or up has an effect on the amount that the hub deflects when put to a side load, but those amounts of 2.8 millimeters in the top illustration and 2.5 in the bottom illustration appear to be the same regardless of whether the tension on the spokes is high or low. So these few experiments, however simple they were, illustrate to us that the amount of sideward deflection of the hub is unrelated to the tension on the spokes. However, as we have seen, it is most certainly not independent of the dimensions of the wheel and the elastic modulus of the spokes.